As I mentioned, Sunday, I'm going to do it very technical. I basically have two things to talk about. We've already talked about them on Sunday, right, in the practice, with a bigger screen. First of all, the unitary slash orthogonal diagonalization. And secondly, the SVD decomposition. Now, I want to elaborate about the SVD from more, I don't know, theoretical point of view, but basically we will show the algorithm, run over an example, and then talk about the more, I don't know, theoretical parts, and let's see how we go. After we're done, I'll talk about the final exam. Nothing really surprising, but I want to. In Hebrew, it's called the Yashar Kav, to make know what are we going to, when are we going to about the final exam, and let's see how we roll. If we finish some minutes before the formal time of finishing, we will be okay, I guess. The same goes for Infi afterwards. Okay, so we defined finder. A matrix A of some order n is called normal if A and A star commutate, semicolon. A is called a Hermitian if A is actually its own star. Okay, now I want to talk about, start to mention it, but now we can show it because we're running out of time. Unitary slash orthogonal diagonalization. I think that's how you write it. Maybe it's just one L, but when I was in school learning English, no, they were talking about they call it CVC or something like that. I mean, when you have uh, two letters and a vowel between them, something like that, then you should double the letter, but I think it's one L. This rule, whatever it is, it's not applying here, not applied here for whatever English reason. Unitary orthogonal diagonalization. Let A be some matrix or a field F. We say that A is unitarily, I don't know exactly how to write down. Unitarily, just a normal U. Diagonalizable if there is a unitary matrix P and a diagonal matrix D such that A is PD P minus 1, which actually means that A is PD P star. Now we know how to find such matrices P and D, inverse matrix P and diagonal matrix D for a diagonalizable matrix A. I want to first today, as Nir Vodish talked about it in the practice, as I mentioned, talk about how can we know that the matrix is unitarily diagonalizable? How can we find such a P in an inverse matrix P, invertible matrix P that is unitary, and how to actually run over the algorithm of finding such P and D. And then we can talk about why is it good? Why is it better than the normal original diagonalization? Um, when P is a matrix at R, the condition P, I didn't mention the orthogonal. Hermitian is fine, but I want to mention the orthogonal. So semicolon A is called unitary. If A minus 1 is A star. Now over R, Hermitian is just symmetric, and unitary is A star is just A transpose because the complex conjugate means nothing above R, over R. And we call such a matrix an orthogonal matrix. In this case, A is called orthogonal. Okay. A is blah, blah, blah. When P is R, the condition P minus 1 is P star is actually P minus 1 equals P transpose. And we mentioned, as we mentioned right now, P is called orthogonal. We call A orthogonally diagonalizable. Orthogonally. Now it may be one or two L's, I don't know, diagonalizable. That is a goal. Is it one L or two L? I think it's two L's, right? Orthogonally. Yes, it's two L. Don't know. Probably it's the Y that doubles the L. Whatever. So two questions, two parallel questions. Given a matrix A in, I don't know, it's C, or generally speaking in F, how can we know that A is unitarily diagonalizable? And if so, how can we find such P and D? And we can ask the same questions about some metrics, in specifically talking about a real matrix? How can we know that A is orthogonally diagonalizable? And if so, how can we find such P and P? So I want to start, of course, with the first question. And I'm not going to prove why is that true. I mean, we're short of time. Yes, no, not the time, not the attention, not the will. We have nothing basically concerning these proofs. So just want to write it down. I'm not mentioning the triangulation. The diagonalization is enough. Okay. So theorem. Let A be some matrix of F. First of all, A is unitarily diagonalizable if and only if the A is normal and it's normal. Now let's write down A, as I write it differently, okay? A is unitarily diagonalizable if and only if A is normal and its characteristic. Well, do we know how to denote it to be A? Right now, the characteristic. Polynomial can be written as the multiplication of linear expressions, linear polynomials. I mean, the condition for the regular diagonalization was that the geometric multiplicity and the algebraic multiplicity are the same for every eigenvalue, and we discussed the minimal polynomial and its linear polynomials that combine giving us the minimal polynomial, but it's the screen is a bit off. But here for unitarily diagonalizable, we need A to be normal and the characteristic polynomial to actually be a multiplication of linear polynomials. What that actually means. So what that actually means over C, every polynomial can be written as a multiplication as such. So we just can say that A is unitarily diagonalizable if and only if A is normal over R. Over R, we can show, we're going to do it, but one can show that normal and can be written as multiplication, blah, 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 actually means that A is symmetric. And A is A transpose. Over R, one can show that normal, which means A transpose commutates with A over R, because the star is actually transpose, and PA can be written blah, 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 is equivalent to A being symmetric. So over R, matrix A is orthogonally diagonalizable if and only if A is symmetric. A in A transpose are the same. So that's the first question. I mean, we answered it without explaining, without proving. I mean, it's good enough for me at that time of the semester. Okay. Um, for the second question, how can we actually find the such P and D? Okay. So by that this theorem, we answered the first question. For the second one, how can we find such P and D? The algorithm is basically the same as in or as for the regular, whatever it is, diagonalization, or the normal, the not so spatial, diagonalization with one difference. First of all, we find the eigenvalues. We put them in the diagonal, and that's the matrix D. Secondly, we find the eigenvectors. That should be the matrix P, but right here, we need them to be orthonormal. When one of the equivalent conditions we mentioned lectures before, the matrix is unitary or orthogonal when you talk over R, if and only if its columns are orthonormal. And the eigenvectors in the usual diagonalization, the regular diagonalization, the eigenvectors are the columns of the matrix P. So, in conclusion, we need the eigenvectors to be orthonormal. So, we choose them to be orthonormal. I mean, as we mentioned before, was election number 3 or whatever, before, I don't know. Every eigenvalue has an infinite number of eigenvectors. We can choose one specifically as we wish to put in the column of the matrix P. Now, we need to choose them to be orthonormal, and by that, we guarantee that P is unitary and over R is orthogonal. No, orthogonal. How can we do so? How can we choose the vectors to be orthonormal? So Very convenient. How? We choose them to be orthogonal to each other. Then we normalize. Okay. As usual, the difficult part of the question is how to make them orthogonal. Normalizing for the orthogonal is the small step. How do we take the big step? So, very nice. How do we choose them to be orthogonal? So, first of all, if A is indeed unitary slash orthogonally, unitarily slash orthogonally, and diagonalizable, then vectors of different eigenvectors of different eigenvalues are automatically orthogonal. Not just orthonormal, not just linearly independent, as we proved earlier this semester, but they are actually orthonormal. The eigenvalues, the eigenvalues, the eigenvectors of different eigenvalues are orthogonal automatically. We just need to choose the eigenvectors of the same eigenvalue for an eigenvalue with geometric multiplicity greater than 1, which actually means he has more than one linearly independent eigenvector, to be orthogonal. For that mission, we can choose whatever vectors we want, as long as they, of course, linearly dependent. Independent problem. Independent, and apply cold water to the burned area. Apply a Gram-Schmidt. It's with C, I think it's with C, yeah. When the C is before the A, but something like that. Schmidt, or just choose them wisely, as we will see in the very next example. I mean, if it's just two vectors, one can choose one and choose the other one to be orthogonal without Gram-Schmidt and blah, blah, blah. Theoretically speaking, you can have a million over million matrix and some eigenvalue has 100,000 eigenvectors. So probably tell the computer, choose it wisely. It's harder than telling to like Gram-Schmidt. They take time, but we can know how to algorithmically put it in words for the computer. But here in a specific case, we do as humans, 3-on-3 matrix, 4-on-4. It's easier to choose them wisely instead of applying Gram-Schmidt. Okay. Let's go for an example. It's a 4-on-4 matrix. It's wrong, but try to shorten the process. Yeah, I mean, it's very shortened here. Maybe we should stick to 3-on-3 something. Okay, now I'll find another example. It's 4-on-4. It's take too much time. Okay, here is the matrix. Any questions before we start the example? Sammy?
Nope.
Okay, so we've already seen it with here, right? So let's look at the following example. A is the following 3-on-3 matrix. Why aren't you going down? Okay. Okay, so A is 3 minus 2, 4. And minus 2, 6, 2. And 4, 2, 3. Okay. So first of all, observe that A is symmetric to M's. So it is indeed orthogonally to L's, right? Diagonalizable. If it was for the complex number, we should call it a unitary, right? But A is a matrix of real numbers, so I'm talking about the orthogonal diagonalization. Now we start with finding the eigenvalues, something we've already done more than once through this, yes, through the semester. 0 should be xi minus a, or lambda, whatever English or Latin or Greek letter you like. So x minus 3 and 2 and minus 4 and 2 and x minus 6 and minus 2 and minus 4 and minus 2 and x minus 3. Let's say we choose to find it using the first row, so it is what it is. This x minus 3 multiplied by the following 2-on-2 matrix. X minus 6, minus 2, minus 2, x minus 3, minus for the second element, 2, well, example here, 2 multiplied by delete the row, delete the column, each one left with x minus 3, minus 4, minus 4, x, no, what? No. Minus 2, that's 2. Do what here? Thank you for making mistakes. Minus 4, x minus 3. And yet again, minus 4. Here, you've got some spacing. Shows the element, the matrix. 2-on-2, it is 2, x minus 6, minus 4, minus 2. Okay. Let's continue. As we know, opening the brackets till the end may not be the best strategy because maybe it's a cube polynomial we don't know how to generally deal with. So let's try to Keep our parentheses closed. Hopefully it will work for us. X minus 3, x minus 6, minus 2. As usual, I'm doing it the long way. You can shorten things. Minus 4, 2, minus 2, minus 4, x minus 6. Okay, 6 minus 3 multiplied by x squared minus 9x's minus is minus 4. No, it's plus 18 minus 4. And minus 2. 2x minus 6 minus 8 minus 4 minus 4 minus is plus 4x minus 24. Hopefully I am not wrong. Now it is x minus 3 x squared minus 9x plus 14 minus 2 2x minus 14 minus 4 minus 4 4x minus 28. Now one can see the common expression. X squared minus 9x plus 14 is x minus 7 multiplied by x minus 2. Minus 4 multiplied by x minus 7. Minus 16 multiplied by x minus 7, as far as I can tell. And we can take x minus 7 out. And we are left with x minus 3, x minus 2, minus 4, minus 16. Hopefully, I am correct at every step. It is x minus 7 multiplied by, no, something's wrong, I can feel it. X squared minus 5x's plus 6 minus 20. Why is it wrong? Because as far as I can tell, it should be some no, it's fine. It's my bad. I wanted the example to contain eigenvalue of geometric multiplicity 2, built from 0, but it's actually it is minus 14. So so it is x minus 7, x minus 7, x plus 2. So we have two eigenvalues. Lambda is 2, minus 2. Geometric multiplicity. We denoted it by D, by a G, because it's geometric. It's 1. And let's use this. And lambda is 7 with geometric multiplicity 2. Here's it 2 times. That's our first step. Usual, nothing different, just like the regular diagonalization. Finding the eigenvalues. Questions?
What you signal there, the manipulate that geometric, right?
Yes. G stands for geometric, which is not very surprising. For the second step, we find the eigenvector. Why aren't you? Okay, it's writing. Now we find and everyone, as we mentioned earlier this semester, can do it whatever it feels like. I like to do it that way. AV equals lambda V, which means that the matrix A multiplied by a general vector, which can be written as x, y, z or something, ABC, alpha, beta, gamma, name it, is lambda multiplied by this vector which means that let's write it down as a system of equations. In the first row, it is 3x minus 2y plus 4z is lambda x minus 2x plus 6y plus 2z is lambda y, and for x plus 2y plus 3z is lambda z. Okay, what do we get for, let's start with minus 2, so this is the geometric multiplicity of 1. We have minus 2 here, and minus 2, and minus 2. Don't think something really convenient here. From the second equation, we do get that 2x is 8y plus 2z. So x is 4y plus z, as far as I can see. Putting that in, for example, the third equation, we get instead of x, we can write down 4y plus z, or instead of 2x, 8y plus 2z, whatever. So it is 16y plus 4z plus 2y plus 3z is minus 2z, which means that 18y is minus 9z. So z is minus 2y, and so x is 4y plus z is 4y minus 2y is 2y. In conclusion, the eigenvectors of lambda minus time are 2y, y minus 2y, as far as I can tell. Hopefully I'm not wrong. And we can choose yet again whatever vector we want, but we need to choose it to be orthonormal to the others. So the others will be orthogonal to this vector automatically. The only problem, the only mission required from us is to choose one that is orthonormal. For example, can look at 2 minus 1, 2, and we normalize. Norm here of 2 minus 1, 2 is square root of 2 squared plus minus 1 squared plus 2 squared. The Lord is merciful. It is 3, right? An integer. But if we are encountering some nasty square roots, it's fine. They are real numbers just like the others. And so the eigenvector is divided by 3, normalized 2 minus 1, 2. This is going to be one of the columns of the invertible matrix, the P, corresponding to the eigenvalue minus 2 in the matrix D. Any questions? Right now, still the same as the regular diagonalization. Still the same.
So, it's orthogonal because of the matrix. We don't have to do something special to it.
Nothing. the eigenvectors of different eigenvalues if the matrix is unitarily / orthogonally diagonalizable are, yet again, automatically orthogonal. We just need to make sure that, first of all, we choose them to be orthonormal, which means normalize them. And secondly, when it comes to more than one eigenvector of the same eigenvalue, what's going to happen right now? Then we need to choose them, as I said, wisely to be orthogonal. Any other questions? So, what are we going to do for lambda equals 7? It's 7 instead of where's the quality? 7. Now, as we know, because geometric multiplicity is 2, I mean, one can be more precise here. The multiplicity that is shown here is actually the arithmetic one, the algebraic one. I mean, 7 appears here 2 times, so it is 2. But we already know that A is orthogonally diagonalizable. So A satisfies the basic condition of diagonalization. For every eigenvalue, the geometric multiplicity and the algebraic multiplicity are the same. So yet again, be more precise, one can say, you know what? A of minus 2s. A of minus 2 is like 1. We can see it here clearly. It appears only one time. And so the geometric is the same, and the same goes for 7. I mean, what we can achieve immediately from the characteristic polynomial is, again, the algebraic multiplicities. The geometric is the number of, it's formally the dimension of the eigenspace. What it actually means is how many free variables we have in the linear system of equation. AV is lambda V.
Yeah, but you can also find it from the minimal polynomial, right? Like the power of the minimal polynomial.
We talked about the Jordan form in lecture 6, lecture 7. And then we somehow, but not in every case, connected between the Jordan form and the degrees in the minimal polynomial on one hand, and the geometric multiplicities on the other hand. But they are not actually not the same. Yes.
Yeah,
So the difference
the biggest block.
block in Jordan form, and the geometric multiplicity is the number of blocks for each eigenvalue. But no, and again, the formal definition talks about the eigenspace, talks about the number of free variables in the system of equation AV is lambda V. But now we know that every matrix is diagonalizable if and only if, for every eigenvalue, the arithmetic multiplicity we denote with A of lambda and the geometric multiplicity we denote with G of lambda are the same. Now we know that A is diagonalizable, and moreover, we know that it is orthogonally diagonalizable, and specifically diagonalizable, because it is symmetric. And because I already know that A is diagonalizable, I can write it down. You know what? This is the arithmetic multiplicities, the algebraic multiplicities, sorry. But we know that they are the same as the geometric one because A is diagonalizable. So what I want to say here, that's because we already know that the geometric multiplicity is 2, we are going to have 2 free variables. Every equation here should actually say the same. Yeah, say the same thing about our equation. Let's write it down explicitly so it can be more persuasive. It is minus 4x it should be 0. It is minus 1y should be 0. And it is minus 4z. It should be 0. And one can see that they are all actually the same vector. So, for example, it's the easiest to express y with x and z using the second equation. Y is 2x minus 2z. And the eigenvalue vectors are x is a free variable, y is dependent, and z is free yet again. And first of all, one can notice that the vectors of lambda equals minus 2 and the vectors of lambda equals 7, the correct here, are indeed orthogonal. Whatever y is, whatever x and z are, you look at the, of course, standard inner product, multiply these two vectors, you do get 0. 2xy plus 2xy minus 2yz minus 2yz or something like that. Yes, one should check that is indeed correct, not something else. 2x minus 2z. No, I'm wrong. It's 2. I check myself or shrek myself because I need them to be orthogonal. So I can say that y needs to be 2z minus 2x and not 2x minus 2z. Let's write it down in a different color. Any preferred color? P, let's look at class. Okay. Observe that 2y and minus 2y on one hand, and x 2z minus 2xz on the other hand are indeed orthogonal. And as I mentioned, it should always happen. The eigenvectors of different eigenvalues are automatically orthogonal. Now, for the wise choosing, how can we need to find, of course, two vectors because we have two free variables, and we need to choose them to be orthonormal, more precisely, to be orthogonal, and then we will normalize them. So, we can choose, I don't know, for example, 1, minus 2, and 0, for example. We get it for x is 1 and z is 0. No.
What are you selecting is vector?
We need, because we have two free variables here. In the regular diagonalization, we need to choose two vectors that are linearly independent. Put them in the columns of P should be invertible, so it should be linearly independent. Now we need something, we need more. We need them to be orthonormal. So it's orthogonal and we normalize later. How can we choose them to be orthogonal? As I mentioned, generally speaking, one can choose linearly independent vectors, just like in the regular diagonalization, and then apply Gram-Schmidt process. But it's not necessary. I mean,
Don't we know that the eigenvectors are orthogonal spaces?
for different eigenvalues. But here we have two different eigenvectors for the same eigenvalue. And here we can choose them randomly, but even if they are linear independent, it does not necessarily mean that they are orthogonal. From here, this is the subspace. I mean, putting it in that way, we have the eigenspace of lambda equals 7 with the span of such vectors. We need to find an orthonormal basis for this space. And as I mentioned, one can choose whatever basis you want, actually means two linearly independent vectors, and apply Gram-Schmidt process. But I think it is easier to choose them wisely. For example, I choose one vector. Now, we need to choose another vector x, 2z minus 2x and z such that that is orthogonal to 1 minus 2, 0. So what do we actually want? We want the multiplication of 1 minus 2, 0, and the x, 2z minus 2x, and z to be 0. And yet again, it's the standard inner product, not something surprising. Very surprising, actually. And what do we have here? It is x minus 4z plus 4x, and that's it. It's 3x minus 4z. Any vector satisfies this condition will be orthogonal to 1 minus 2, 0. For example, we can look at the vector where x is 4 and z and 3. Instead of and so the second vector is x is 4, 2z minus 2x is minus 2, and z is 3. Yet again, this is the vector, yes? So choosing x to be 4 and z to be 3 leads to the following vector, 4 minus 2, 3. If I'm not wrong. And one can check that, yes, the vectors 1 minus 2, 0, and 4 minus 2, 3 are actually orthogonal. And on the other end, of course, both are of the shape of the form x to z minus 2x and z. Both are actually eigenvectors of lambda equals 7. We need them to be orthonormal, so let's normalize. Normalizing, we get, and here the norm is square root of 5. Here it is 16 plus 4 plus 9, which is the square root of 29. We may choose the numbers differently, but not now. Hopefully I'm not wrong here. 4 means 2, 3. Okay. So in conclusion, our matrix A is PDP means had, which actually PDP transpose. Where D is the matrix of the eigenvalues in the diagonal. Let's say we start with minus 2 and then 7s. We know one can choose them in whatever order he wants to put them in. And C is the matrix of the eigenvectors in the column. So the eigenvector of minus 2 is this one. It's 2 above 3. It is minus 1 above 3. And 2 above 3 again. And the two vectors of 7 in the other two columns. It's 1 above square root of 5, minus 2 above square root of 5, 0, 4 above square root 29 minus 2 above the square root of 29 and 3 above the square root of 29.
Yesterday, like, on Sunday, what I thought is that it's very important to give the order of the vector on B, right?
Just as in the regular diagonalization. I mean, if we put minus 2 in the first column of D, then the eigenvector of minus 2 should appear in the first column of P. Then this is the importance of keeping the order straight. Of course, one can check that P, D, P transpose is actually A, but it is not needed. It's enough to find P and D. And for the advantage, what is better in the unitary / orthogonal diagonalization? What is better than the usual regular diagonalization? Well, first of all, calculating P, the inverse of P, is peanuts. We just transpose it, or transpose and conjugate when when it comes to complex numbers. And moreover, we've already talked about the advantages of unitary matrices, that they preserve angles and distances and so on. So it is better. We can do it if the matrix is not just diagonalizable, but it is unitarily / orthogonally diagonalizable, to do it using unitary / orthogonal matrices. Okay. Any questions about that?
Because higher than two, like 3 or 4 or whatever, and you need to find the orthogonal eigenvectors for the same eigenvalue.
Yeah.
Do you just ask equations or?
So yet again, it doesn't matter what the number of eigenvectors needed is. We can find a basis, linear dependent vectors, and then apply Gram-Schmidt. Or we can find them, as I called it wisely, one by one, choosing some vector, then the other one to be orthogonal to him, then the other one to be orthogonal to them. And yes, it will be a system of equation.
Apply the inner product and just check that it's 0.
Yes.
Again, no, yeah, but also like if you have more than 2, 3, 4, whatever, you need to like check all of them. So that's when it's better to do fine.
We can do Gram-Schmidt, yeah. As we want, whatever we want, but let's talk real. When it comes to a question in the final exam, it can't be a 6-on-6 matrix with eigenvalue of multiplicity 4. You spend your all 3 hours of the exam on one question. So as usual, 3-on-3 or easily 4-on-4 are the cases we should expect. And when it comes to 3-on-3 or 4-on-4 matrices, I'm not going to have one eigenvalue with multiplicity of 4. Okay. Any other questions? Okay. Our second topic for today and the last topic for the semester is the SVD decomposition.
Yeah.
Yes, you saw everything with here. Means the last practice, so it should be it should be as it was. Decomposition. It's a new topic in the syllabus. Adi taught it in the last semester B. I'm not sure if it was in last semester A, but 2 years ago, I think it was not on the syllabus of linear algebra 2. It was added because it is important for some of the advanced courses of machine learning, deep learning, artificial intelligence, and so on. So we will yet again explain the algorithm technically, and we will show one example, and then we may shortly discuss the advantages of such a composition. Then we talk about the exam, then we can move forward, march forward to infinite. Of course, we are close to our break, so we take it shortly. Okay, let's be a matrix. Notice that the number of rows can be different from the number of columns. It's not our square and nice matrices we discussed in the last topic. We want to unitarily slash orthogonally diagonalize A. Of course, it cannot be done because A is not necessarily a square matrix, but we can. What do we actually want? We want to find U and V, or orthogonal unitary slash orthogonal matrices U and V, and a diagonal matrix will denote with the letter big sigma such that A is U and sigma V star, where U is M on M, V is N on N, and sigma is M on N. Sigma is M on N. What do I mean by diagonal matrix if it is not a square matrix? Yeah. Sigma by diagonal we mean that the ij element of sigma is 0 if I is not j. I mean, for a quick example, the following matrix, it'd be some different number, 7. The following matrix is diagonal, because every element that is not on the diagonal is 0. Now the question is, how can we find such matrices? And we will show an example, and then shortly to discuss what can we do with such decomposition. Okay, this is the mission. Let's take our break, 15 minutes break. And as we return, we will describe the algorithm to find such U sigma V star, and then we will show an example. I stopped the recording. I actually pausing it. Resume recording. Okay. So I want to, as I mentioned, show you the algorithm. how can we actually do it? And right now we can think about the cases where we have more rows than columns, and then we will explain how can we do it when we have more columns than rows. Rows. So um, first of all, just for theorem, okay? The theoretical part. Every matrix has an SVD decomposition, such U and V and sigma. We call such multiplication U sigma V star. We call this multiplication SVD. Oh, no. Yeah. SVD decomposition. Not saying that every matrix A has only a unique decomposition, but it has a decomposition. It's single values, whatever. Decomposition. So actually, when you write down the SVD, you actually say the word decomposition twice. Yes. Let's check it out. Yeah. The SVD is a singular value decomposition. So if you write SVD decomposition, is actually singular value decomposition. Yeah. Yet again, singular value decomposition. The algorithm. Let A in M on N, where M is greater than N. We will explain later what do we do where it is the opposite. Now we follow the following rules of the algorithm, steps of the algorithm. First of all, we look at A star multiplied by A. Okay. A star multiplied by A. Semicolon. We unitarily / orthogonally diagonalize it. A star A. What does it mean? We find we find diagonal matrix D and unitary matrix A such that A V such that A star A is V D V star. We've already shown an example how to do so. We order the eigenvalues values by, first of all, we put the biggest one in the first column, and then the second largest in the second column, and so on. And we know that we need to put the eigenvectors SV in the same order. Now, for sigma, we put the square roots of lambda I in the diagonal, and we add rows of zeros to get M1N matrix as much as needed. And of course, we'll see an example shortly. We look now, denote, we look at the multiplications of A with the ith column, that's how we say it, of the matrix V. Okay? Some of these vectors, let's write down where CIV is the I and column of V. We look only at the vectors A multiplied by Ci of V that are not zero. We calculate them. We complete the vectors from our third step, A multiplied by CIV without the zeros, to a basis of the field Fm. And we do it for an orthonormal basis. Orthonormal basis. The vectors we get are the columns of U. And so we have U. Finally, A is U sigma. Where is it? U sigma star. This is the algorithm. Now we've already seen an example with veneer, and I want to show it to you as well. Another example. And then we can see what exactly we mean by every step in the algorithm. Okay. By Allah, yes. What now? Let's note before the example. Note F over R instead of unitary, it is orthogonal, and so on. Basically the same as we already seen. Okay, now, for example, let's go through the following example. Blah, blah, blah. I have here -3. One, 6 minus 2, 6 minus 2. Okay. Let's do it step by step. We look at the matrix. What happened? You still look there. A star A. Well, A is a real matrix, so star only transpose it. And the transpose of A is -3, 1, 6 minus 2, 6 minus 2. what do we have here? It's a 2 and 2 matrix. That should be. And the first element, minus 3 by 3 is 9. 6 by 6, 36, 36, 9, 36, 36 is 81. Minus 3, minus 12 is minus 27. Minus 3, minus 12, minus 12, minus 27. And 1 plus 4, that is 9. The matrix here should always be Hermitian, which means that it can be unitarily diagonalizable. When it comes to R, it is symmetric and it is orthogonally diagonalizable. We find and we orthogonally diagonalize it. First, eigenvectors, eigenvalues. Who are the eigenvalues? Okay. 0 is xi minus a star a, which is the determinant of following to draw to matrix. It is x minus 81, 27, 27, x minus 9. Now it is x minus 81 multiplied by x minus 9 minus 27 multiplied by 27. It is x squared minus 90 x plus 729 minus 729, which is x squared minus 90x. And we have 2 eigenvalues, 0 and 90. Yeah. Now for eigenvector, secondly, we find a ortho normal eigenvectors. Notice that we have only one vector for each eigenvalue, so and they will be orthogonal, so we actually just have to normalize, and that's it for getting what we have. A star A with V should be lambda V, which means here in this specific case that this matrix multiplied by x and y is should be lambda y. Means system of equations. No, that's why. For the first equation, we have 81x minus 27y should be lambda x. And minus 27x plus 9y should be lambda y. So for lambda equals, what do we have here? 0. We get 27y equals 81x. Yeah, Sammy. Whatever you like. Finding the eigenvectors, as we said through the semester long, whatever you like. Matrix manipulation, science, whatever. Find them. I know you know how to solve such simple system of equations, so you do as you do. Okay, so we have well, y is 3 times x. And the vectors, the eigenvectors are x 3x. For example, 1, and 3. And after we normalize it, it is the square root of 10, right? Square root of 10 of 1 and 3. What do we have for lambda equals 90? Let's copy, let's paste, and change the rest. It is 20 x's, it is 20 y's. So one way or another, it means that x is minus 3 times y. And so the vectors look like minus 3 times y and y. For example, minus 3 and 1, and we normalize the get. It's still the same norm, but different vector. Minus 3 and 1. This is our first and probably the longest part of SVD. We find D, we find V, and we organize the eigenvalues from the bigger to the smaller. So in conclusion, for the first step, the matrix V is the matrix. Let's take this square root of 10 outside for a walk. And the vectors are, we put the bigger one first, which is 90. So the vector of 90 is minus 3 and 1, and then the vector of 1 and 3. One can write down explicitly what D should be or what sigma should be. Any questions, other questions about our first step of finding V? And minimum?
I mean, we didn't prove, but now I'm not going to prove like say star and say and all of that.
Why is it working?
Yeah, we're not proving why it works.
No, don't have the time. Let's say if we did have an additional lecture, in a different constellation, it could happen. If we had, for example, lectures on, I don't know, Wednesday morning, which should be 14 this semester, you could have explained it. It's not very difficult. You know, the multiplications are going to be zero very, very nicely, but it takes time we don't have. And now going to the second step for sigma. So for sigma, the matrix should be 2 on 3, 3 on 2 matrix, just like A. In the diagonal, we put the square roots of the eigenvectors from I don't know, big to small, from greatest to smallest. And we add rows of zeros. So in this case, the matrix sigma is, no, the other way around. Square root of 90, 0, 0, 0 again, because it's the second eigenvalue. And we add a row of zeros just for sigma to be as the same size as A. So this is the second step, writing down sigma. Okay. Any questions about our second step? Okay. For For the third step, we look at A multiplied by CIV. We calculate A multiplied by CIV. So A is this matrix. And we know what the columns of V are. So A multiplied by the first column of V is A multiplied by 1 above the square root of 10 and the vector minus 3, 1. Well, the square root of 10 can stay outside. These kind are not welcome here. And when we multiply the matrix with the vector, minus 3 with it is 10. And here it is minus 9, 18, minus 12, which is minus 20. This minus 20. One can write it down without the square root of 10. Don't know if it's necessary right now. And we have a C2 of V multiply A with the second column of V, which is 1 and 3. And minus 3 minus plus 3, which is 0. 6 and minus 6, which is 0. And 0 all over again. And as we said, we do not look at vectors that are 0. I mean, in the description of the algorithm, we look only the vectors that are not 0. And in the fourth step, we complete these vectors to an orthonormal basis. And if the vector is not normalized, which is not the case, we of course normalize it. So for our fourth trick, now we complete the vector of, well, write it down as a row instead of a column because it's easier. Row with the commas, it's actually a column. We complete to an orthonormal basis. Of course, we need to normalize it. How do we complete a vector to a basis, not mentioning orthonormal basis? So, generally speaking, we can write down the vector as a row in a matrix or a column and add vectors that are linearly independent. For example, one can add 0, 1, 1, 0, 1, 0, and 0, 0, 1 or something. But such vectors won't be orthonormal. So yet again, we can choose a vector that is to complete it to a basis, then just a basis, and then apply Gram-Schmidt, or we can choose the vectors as again wisely. So yet again, we can complete it to a basis and then apply Gram-Schmidt. Or we can choose the vectors wisely, whatever floats your boat. Here, for example, first of all, let's normalize. The norm of 10 minus 20 minus 20 is the square root of 100 and 400, which is 30. So the vector normalized is actually the vector here, where the norm of the vector with the square root of 10 is, we know that the norm is multiplicative, meaning that a scalar can get out, at least with an absolute value, but it's a positive number, so it doesn't really matter. It's 1 above square root of 10 multiplied by 30. And we have, instead of the vector with the square root of 10, we normalize it. So it should be divided by its own norm, which is 30 above the square root of 10, which leads to a nicer vector without any square roots. It's third and 1 minus 2 minus 2. This is the vector normalized. Now we want to find two other linearly independent vectors, linearly independent with this vector, that are orthonormal. So we can choose it wisely. Now we look for, I don't know, a vector ABC such that multiplication of 1 minus 2 minus 2 and ABC is 0. Yet again, I can choose the basis and then apply Gram-Schmidt. Is 0, which means that A minus 2B minus 2C is 0, and A is 2B 2C. For example, it can be, I don't know, 2, 1, and 0, and normalized, it is the square root of 5 with 2, 1, and 0. And again, after we find this vector, now we look for a vector ABC that is orthogonal to both of our vectors, to 1 minus 2, 2, and to 2, 1, 0. And notice that I don't really care about the scalars when I check for orthogonality, because the multiplication will be 0 with the square root of 5, without the square root of 5, nonetheless. So the multiplication of minus 2, 2 would be 0. And the multiplication with 2, 1, 0 should be 0. And here, yet again, it's A minus 2B minus 2C. And it's 2A plus B equals 0. So, for example, one can choose A to B minus 1, B to B 2. And then if I see it correctly, no, let's do bigger numbers. We normalize it, so what does it matter? For example, what vectors satisfy both conditions? If I take A to B minus 1 and B to B2, then C has to be some, well, let's do it with minus 2 and 4. If A is minus 2 and B is 4, then C should be minus 5, as far as I can see. Check me before I wreck myself. I think it's good. And normalized. we get the following. It's 4 with 16. It's square root of 20 or 45, as far as I can see. In conclusion, the vector, it's the fifth, no, still the fourth step. The vectors we get are the columns of U. We did get the vectors here. So it is, where do you write it? The 3-on-3 matrix. This is U. The first column is the first vector. And here is the second one. It's with the one with the square root of 5 in the denominator. And here it's the 45 one. And finally, I claim that A is U sigma V star, which, real number speaking, it is just V transpose. Where is sigma? It's a sigma. And this is V start. Of course, one can check that this beautiful equation does actually holds, but it is not necessary, and it's all very tiresome, especially this one. Okay, so it's very technical. I'm not saying it's nice or pretty, but it is technical. And I want to say, what can we do when A is not with M smaller than N? It's basically the same, but still. And then we can talk about the exam and finish the job here. Any questions about the algorithm and how we applied it here?
Why? But
Yeah, it's technical, sometimes ugly, but
I mean,
nothing here is, I mean, needs of us some thinking, you know.
the benefit of it is that you can theory like get from any size of matrix to any size of smaller matrix, or especially don't matter.
Come again?
Like you can get from any size of matrix of square matrix to any size of other square matrix, right?
No, it's the same. The middle matrix is the same as the matrix we start with. I mean, the sizes of the U, sigma, and V are dependent on the size of A. We cannot choose whatever size we want. And any other questions? Okay, so I want to note two things. Sammy, any question? Still with us? Hope it's good. I mean, still connected though. Um, let's write down two notes. First of all, or A, if A, if the number of rows is smaller than the number of columns, we can look. Oh, somebody wrote something. Oh, exactly this one. Trying to answer. Great minds think alike. How do you say this phrase?
I think that's never later.
What?
The whole phrase is a bright minds think alike, but idiots never differ.
Um, I wasn't familiar with the second part of the phrase. And secondly, I just saw the Infi 1 students in Hebrew in the first semester that all the good solutions for exam questions look the same, but all the wrong one has each one with color, we say in Hebrew. Each one with a different color. You can come, you think, time should come where I've already seen every possible mistake for the same question. But I'm surprised every semester. I'm surprised. How can you, on both sides of mistakes? I mean, on one hand, some gentle, tiny, thin mistake. You're almost there, Mr. Student. Another epsilon close to the good solution. And on the other hand, some horrid bullcrap. I mean, how could you possibly think of that? Did you actually study the material? But you're good students. You will succeed. And let's finish the material and talk about the exam. If m is smaller than n, we can look at a star or a transpose when it comes to real numbers and find its sorry. Find its u and sigma and v, and then if a star is some u, sigma, and v star, then if we star both sides of the equation, on one hand, we will achieve A, on the other hand, we will have starring the switching the order, and we star every matrix. So V star star is just V, and sigma is starred here, and U is starred, and it's basically the same SVD decomposition. U and V are orthogonal, and inside in the middle, a matrix, diagonal matrix should be the same. So this is the first thing I wanted to say. And so the algorithm is basically the same, just star it in the end. And the second thing I wanted to talk about the SVD decomposition. Has various important uses. No, but to actually put it in words. And for example, finding what is called the pseudo inverse. So should I write it? Pseudo inverse of A. What is the pseudo inverse of a matrix A? For what is pseudo inverse? Just want to speak about it. What is pseudo inverse? let's say we want to solve A multiplied by X is B, a system of linear equations. Now, we know that if A is invertible, we can multiply both sides with the inverse of A and find X. If A is square matrix, and we know that the system has only one solution, we can find it by multiplying both sides with the inverse of A and achieving X solution as A inverse multiplied by B. You've already probably seen it in the first course of linear algebra. Now, when the matrix is not a square matrix, we cannot talk about A squared, but what can we do talk about? We can look at I just don't want to elaborate too much about it. When A is not square matrix, we can use the pseudo-inverse matrix. Now define it.
Well, I think it's
PSEU. Pseudo
I think.
or pseudo? And then pseudo, yes, you're right. Pseudo. Pseudo, and change for pseudo as well. And pseudo again. We denote it with A plus or something, okay? And it is, yeah, let's write it. If A is U sigma V star, then the pseudo we denote with A plus is V sigma plus U star. And what is sigma plus? Where sigma plus is the inverse of sigma. Every non-zero value A in the diagonal is becomes 1 above A, and we transpose. For example, if the matrix A is written that way, then the pseudo inverse of A which I denote with the plus is V without the star, U with the star, and for the multiplication to work, sigma should be not 3 on 2, but 2 on 3 matrix. And instead of the square root of 90, you look at 1 above the square root of 90. we call this matrix pseudo-inverse. And when we have the pseudo-inverse, in this case, not in the specific case here, but generally speaking, if we know that AX is B, and we multiply it with the pseudo-inverse, multiplication of the pseudo-inverse with the matrix itself is something that it is somewhat easy to calculate. It's not, they do not cancel each other as the actual inverse cancels with the matrix itself, but they do cancel each other. I mean, U star multiplied by U is actually I, because U is orthogonal, and its star is its inverse. And we are left with V sigma. And yet again, for this example as well, if you multiply sigma plus with sigma, it is not I, but it is similar. You will get 1 and then zeros. And then V with V star is also I. So you get, you don't get X itself exactly, but you get something close to it. When it comes to reality, this approximation is somewhat very good. And yet again, the SVD decomposition has many various important uses all along mathematics, statistics, signal processing, you name it. Specifically, in, as I mentioned, advanced course you will encounter when you continue your journey through your studies. I don't want to say exactly where, depends on the lecturers, but it is can be connected to deep learning, machine learning, artificial intelligence, and all these nice buzzwords. It's not very important to us. Don't be afraid. We're not afraid of the pseudo inverse. Just an example for a use. And you will probably encounter the pseudo inverse as well when you go to the more advanced computer science courses. Okay. Any questions about the mathematics we studied today or throughout the semester? Yeah.
So many questions, not enough time to answer them myself, but yeah.
Yeah, it's probably true for every course. So now let's talk about the final exam shortly. You're not, it's not your first semester, your first radio. You know how it technically goes. You go to the class, you have these, in Hebrew we call them the ants. Dodot. The ones who actually look at you when you take the exam, yeah. So not enough to can't take you about that. The exam is at the 2 weeks from now. Yes, it's 12th to February. So I need to write the exam. I probably won't do it today, but in the tomorrow. But till Motzash, I will do it. The exam will contain 5 questions. Each one is 21 points. May contain some parts, sub-questions. The questions are going to be similar to the examples we did in the lecture, you did in practice with Nir, you did in your homework. It's not something new. It's not going to be the same exam as the exam of the Hebrew group. Not going to talk with a D and so on. So I don't know if it's the same date as well. And most important, something important, you need to pass the exam to get at least 60 in order to pass the course. It's not my decision. I prefer the decision your way. You get the total 60, considering the homework and so on, but this decision got decided for me. So you have to get 60 in your exam in order to pass, and then the homework will be applied and probably help you get you another 1 or 2 points. I'm not trying to promise anything, but the exam shouldn't be very hard. You should solve the homework, look at the lectures, the practices, and probably solve exams from previous years. I don't know how to find such in English. I don't know if there were such exams in English. Are you the first class, the English class here?
Yeah, and maybe the last.
Maybe. Let's see. I don't know.
I can talk to them because I don't understand why they can make like multiple times. We teach computer science and Hebrew. That's like the perfect program for people that are new to the language. So I don't know.
Yeah, you told me you started 20, now you're 5 or something. So
Yeah, we started looking at numbers.
yeah, something can be improved, but I agree that the idea is basically good. The exam is 3 hours long. If you have some additional time, what?
3 hours.
3 hours. What did I say? No, 3 hours. So 3 hours long, 180 minutes. If you have additional time or something else like that, you're welcome. It's not going through me. It's going to the administrational part of the university, the secretary, I don't know, whatever, take care of it, whoever take cares of it. You can enter, you can come with a calculator, the normal one, the one that can, yes, the one that do calculate, there's some calculators that can draw graphs and stuff. No, no graph, no. Yes, it's not for this course, but it's the same for if you too. I mean, if you want you to calculate integral, I want you to show me the way you do it. So yeah, so really helpful, but for the numbers, etc., you can use a calculator. We don't have a formula sheet. If some of you or all of you, I don't know, have a specific I don't call it benefit. You do have the right to enter the exam with a formula sheet. You should talk to me and I'll send you something I'll make myself. But the default is without a formula sheet. You don't get it in the exam as well. Me or Nir or both of us will visit you in the exam. You probably be only one class. Hopefully, you're not going to be separated for the 407 or 101 or whatever. And so we'll try to visit you more than once through the exam, and I hope we will be able to do so. But no. When you get to the exam, you look at all the questions, and then you decide, okay, I understand this question, I don't understand the question, and you can ask us when we actually come. Because you're a small group of students, I hope that the scanning of the exams to the system and the checking of the exams should be very long. So if the exam is on Thursday, I hope that on, I don't know, next Tuesday or something, you will have your grades, and hopefully they will be good ones. What else? What else? Everything is true for term A and for term B as well. I mean, 5 questions, each one is 21 points. I'll try to what's I try to put every subject that we learned in the exam proportionally to how much time we learned it, we studied it through the year. I mean, if we studied 2 lectures about determinant and 2 lectures out of 13 is something like a sixth of the material, so sixth the exam should be on determinants. But on the other hand, we know that the subjects are mixed with each other. I mean, we use determinants here right now, of course, so it will not be exact, this partition. What else? Any question? Thomas, Sammy, about the exam or what's going on? So how do I recommend to prepare? First of all, go through the lectures and practice one time. Don't have to do it very thoroughly, and then solve the homework again, and then go through past exams. If you did all that and you solved all the past exam of the, let's say, last 3 years, which should be at least 4 exams for every year, because we have it at semester A and semester B as well, you should be totally fine. Shouldn't be any surprise for you.
Do you usually prepare the exams for the Algebra 2 or?
No, as I mentioned when we started the semester, it's the first time I teach as a lecturer linear algebra 2 at all. I mean, I wasn't not Hebrew, not English class. But yet again, the questions will be similar to this question of the homework, lecture, and practice. Nothing different or very new. Any other questions? Okay, so we can finish with linear algebra and take a break as we usually do. And we do the same for infi. We need to study some new material, how to change variables of double integrals. And then we will, why did you get out? I don't know. And then we will talk about the exam of infi as well, but probably be the same sentences I told you today. Okay, have a nice break and meet you at